Thanks, folks, for coming. Today, Neha and I here from Apple, we're going to talk a little bit about the journey we had from moving our Spark workloads from legacy Hadoop clusters and overall to the Kubernetes kind of ecosystem a number of years ago when Kubernetes was maybe not as nice as it is today. So you'll hear some war stories there as well. So in terms of agenda, we're going to talk a bit about going from bare metal to Kubernetes and how we had to evolve kind of Spark techniques over time to make that work. And you'll kind of see like we went through one other type of compute story in between, going from bare metal to Kubernetes. And then ultimately now being on Kubernetes with the advanced scheduler like Unicorn. Also super excited to learn about all the developments in Q, and that those have kind of come along in the last couple of weeks. And then kind of key takeaways for like making Spark work well on Kubernetes, because traditionally Kubernetes is not built for, let's say, data-intensive workloads. So we'll talk a little bit about best practice and pitfalls and anti-patterns to kind of stay away from. In terms of objectives in the migration, is like we have a lot of data engineers and data analysts who are using Spark, and they need interactive access to large data sets. We really kind of want to separate storage and compute, kind of that disaggregation over the last 6 or more years, right? Being able to put your data in cloud storage or some storage system that doesn't have your compute coupled to it gives you a lot of flexibility. Then we also will talk about cluster autoscaling and then containerization and dependency management. And then ultimately, like better resource utilization is a very key part of this to allow us to kind of reduce cost and then automating as much of this as possible. So with that, I'll hand it over to one of our best minds, Neha, to tell you more about this journey.
Hey everyone, my name is Neha Singla. I'm a software engineer at Apple. Thanks for sticking with us this evening. I appreciate it. I know it's been a long day. So I'm going to talk about some of the special requirements with Interactive Spark. So Interactive Spark plays a crucial role in like big data processing, data science, and machine learning workflows for faster data exploration, debugging, and ML experiments. And Jupyter Notebook is one of the popular tools used in industry for Interactive Spark experiments. So here I'm going to talk about some of the unique requirements which Interactive Spark brings in. So Interactive Spark needs to provide low latency responses for querying and processing large data sets. This helps data scientists and analysts to iterate faster on their experiment and without waiting for them for long-running batch jobs. Pod launch latency matters in interactive cases where you don't want your users to wait longer for running their experiments. In a multi-tenant environment where users are sharing resources, real-time monitoring as well as introspection of queue events, pod logging, Spark UI, messaging into live notebooks, robust connectivity becomes extra important to track usage and to prevent bottlenecks between resources. And there could be special requirement for non-preemptive workloads, like you need to provide a Jupyter environment, which you don't want that to be preemptible, which is different than the normal batch processing system. We need fair resource allocation here, which ensures that no single user monopolizes the whole cluster. Minimum resource guarantee ensures that each user is guaranteed to have some resources for starting their Interactive Spark experiment. So let's start with our baseline Spark on bare metal, which is a traditional deployment model right now. So when we started, as you can see in this diagram, we have a classic setup with a name node, a resource manager, and worker nodes running on the physical servers. In this configuration, there is no virtualization layer. Everything runs on the physical hardware. Compute resources are pre-allocated by admins, and they have to manually manage like node provisioning, scaling, and fault tolerance. And it used to run for us on a very popular resource manager, Yarn. which handles job scheduling, resource allocation, and monitoring to distribute Spark workloads across available worker nodes. It can dynamically scale executors based on the workload demands and support shuffle with external shuffle service. Yeah. A bit more about Yarn. So Yarn is a core component of the Hadoop ecosystem. It allows multiple applications like with Spark to share cluster resources efficiently. It is important to note that Yarn was not designed to orchestrate any containerized application, but specifically designed for orchestrating applications within Hadoop. It would provide a fine-grained access control over CPU memory. It manages the cluster resources using a queue-based architecture to ensure fair and efficient resource allocation. Admin can set resource limits and priorities for different queues to balance their workload demands. There's a great advantage of external shuffle service which Yarn brings in. It helps to maintain efficient data exchange between executors, ensuring better fault tolerance and reducing memory overhead. It can handle large-scale clusters and can be scaled horizontally to accommodate increasing resource demands among multiple users and applications. Let's talk about the challenges. So we face significant challenges with this approach by running Spark jobs on bare metal. One, there was no dynamic scaling of cluster resources. Admin had to provision resources for peak demands. And storage and computes were tightly coupled, limiting flexibility. Each cluster had access to the HDFS storage connected to that cluster only. And for that reason, admin had to write distributed copying jobs for moving data from one cluster to another cluster, and which needed SRE supports, to keep the data consistent between multiple clusters. So they had to write more and more backfilling jobs. There was no data lake concept. Everyone was just querying the raw data. No fault tolerance. One job could bring the whole cluster down and impact all other users. There was no built-in orchestration. We had to ship entire Spark distribution on bare metal, which was error-prone and had connectivity issues. For interactive experiment, there was no notebook interface. Everyone was using a shell interface for running interactive queries, which limited our data scientists' productivity. Our first evolution was moving to virtualized environment using VMware. This introduced virtualization support, giving us more flexibility. We gained on-demand scalability, though not fully dynamic. We moved from Yarn to Mesos-based resource scheduler, as our deployment model was supporting Mesos. At this stage, we had to use static resource allocation because Mesos was not supporting dynamic allocation. We introduced Jupyter Classic for interactivity, which was a significant improvement for our data scientists. We introduced, at that time, data lake concepts where HDFS cluster had network connectivities, and same Spark job could access more than one HDFS cluster. We carved out Hive, Metastore concept. We introduced iceberg tables. We supported table-level queries. Talking about the challenges, despite this, we still face a lot of challenges. The resource management was still problematic. We often saw over-allocation and underutilization of resources. So our administrator has to track all the usage of all the resources. They used to carry like huge spreadsheet mentioning, okay, what type of workload is used where. So it was pretty heavyweight. Our t-shirt sizing were not correct. For a specific amount of CPU, we were allocating large chunk of memory, and people were not able to get resources due to low memory presence. And most people were not efficient in writing their Spark queries, and they were using a lot of memory-heavy data frame. We adjusted the ratio of our t-shirt sizing, which helped a little, but still an issue due to lack of dynamic allocation, due to which sessions could not shrink. On the interactive side, the Jupyter kernel configuration, we were not persisting, and it was not shareable, so everyone had to write their own set of Spark properties on their own kernel configuration, even though running for the same experiment. Moving on, the next evolution was moving to Kubernetes. So as you can see, in this Spark cluster is running inside a Kubernetes cluster using Kubernetes to manage Spark resources instead of Yarn or Mesos. Spark driver here runs inside a Kubernetes pod, and Spark executors runs inside a separate Kubernetes pods. And the entire environment is managed by Kubernetes, giving us more flexibility and standardization. And Kubernetes dynamically manages these pods, scaling resources up or down as needed. So as we know, Kubernetes is the standard for deploying containerized applications on cloud. And Kube Scheduler is the default Kubernetes scheduler, which runs as part of control plane. It has really important characteristics and features to understand and to find feasible nodes for identifying where your application can run. And it gives pretty good knobs like taint toleration, node affinity rules, node selectors, which you can use to define where your application needs to run. It's primarily designed for microservice type workload, node batch data processing. And it uses a spread scheduling approach to distribute your workloads evenly across available nodes. It has a scale-out architecture with auto-scaling capabilities. It operates at pod level and has somewhat limited functionality, but it was designed to be replaceable, which becomes relevant later in our journey. For interactive Spark analysis, we introduce Jupyter Lab, which is essentially an in-browser IDE to enable data scientists and analysts to use notebooks, allowing them to build narratives using both code and text in the same environment. So the screenshot is of the Jupyter Lab environment here. And then users can create multiple notebook files and then run Spark kernels, either in PySpark or Scala Spark or a pure Python kernel to power their notebooks. We built kernel configuration management system for managing the kernel configurations. So we extended Jupyter kernel and supported a Spark kernel where all Spark properties can be added. And it includes both shared and default resource configurations, security configurations, data access configurations. As we know, Spark properties are huge in numbers. So it was important for us to not overwhelm a user who really wants to just run some simple Spark experiment, as well as allowing admin or advanced users who wants to look at the properties and tweak some of the advanced configurations. So we built capabilities to hide those configurations based on the user, and then as well as allowing them the flexibility to tweak their configurations. And our kernel configurations are organized as a hierarchy for easier management of properties and to support different versions of Spark. And then we flatten that in our meta store for implementation simplicity and to better use them in the Jupyter environment. So now, talking about the challenges. So with this model, there were a few challenges. One, as we know, the Kube Scheduler was not designed for batch workload Spark, as it's not app-aware scheduling, and it doesn't have queuing support. So without queuing management and borrowing of resources from each other, it was not as effective for interactive batch use cases. There's no support of gang scheduling, especially like libraries like XDBoost, where we want all executors to come up at the same time, and you don't want to leave them either, is something which is missing in Kube Scheduler. And interactive use cases, like we needed fairness, preemption, reservation, resource guarantee, and resource guarantee for better user experience, and bin packing for better utilization of cluster resources. So those were the things which were not available in Kube Scheduler. And then we faced challenges using Kube Scheduler for Spark interactive workloads. And for kernel configuration management, we built the system which is outside of Jupyter Lab. So now users have to tweak their configurations in one system, and then they have to use that in Jupyter Lab, which was kind of created a friction for our data scientists. So this brings us to our current architecture, Spark on Kubernetes with Unicorn. As you can see here, Unicorn sits as a specialized layer between Kubernetes control plane and our Spark applications. It provides yarn-like scheduling capabilities with Kubernetes, giving us best of both worlds. It provides hierarchical resource management with guaranteed resource quotas per queue. This architecture maintains all the benefits of Kubernetes while addressing the scheduling limitations for Spark workloads. Talking about Unicorn Scheduler, so it can work with any kind of workloads through port annotation. It provides hierarchical quota management. There's no custom resource definition is needed. It completely replaces the Kube default scheduler, handling both queuing and scheduling. It supports priority, preemption, FIFO, fair sharing, gang scheduling, resource borrowing, exactly what we needed for Spark. So this is our current architecture. Here, you see, in this model, we are leveraging node pools and unicorn queues. We have divided our workloads into 3 node pools. The top one is node pool where we want to run our long-running Jupyter server, which is providing an environment for data scientists where on Jupyter server, they can launch kernels to run their Spark jobs. Since it's a long-running, it doesn't scale up or down. It's mainly just one port. So it is managed by the Kube default scheduler. And then the driver, the Spark driver, and is part of a different node pool too. And the third node pool 3 is for Spark executors, and which are preemptible, and then they can scale independently. So with this architecture, it provides us the workload separation, grouping them based on the similar configuration, and streamlining lifecycle management for each type of workloads. The other advantage we see here by putting the driver and executors in the same network zone, it helped us providing better shuffling and the reduced in shuffle latency. So we improved our interactive Spark experience here with further improvement with Jupyter Lab. So we built in a Jupyter Lab plugin for kernel configuration management to reduce the friction and to allow users to do everything in the same environment. We made the improvement in Jupyter kernel connectivity. So it used to happen that user has launched a Spark kernel from Jupyter. The Spark kernel is running, and the port is up and running behind the scene, but Jupyter Lab doesn't have connectivity to connect to that kernel. So we improved the kernel connectivity layer to show the exact status of the Spark driver kernel, which is running on Kubernetes. And we gained queue utilization transparency, giving users better visibility. So overall, this created a much more seamless experience for our data scientists. This slide shows our Jupyter Lab kernel configuration interface, which provides a more integrated experience compared to our previous setup. So you can see here, so this is a Jupyter Lab Spark kernel, where all the Spark properties are configured, and the same can be used to launch the kernel by staying on the Jupyter Lab environment. So we have different presets. There's a minimal preset. This is only for just a smaller set of properties, and if the user goes to the full preset, they'll see an advanced set of configurations only if they want to see it and tweak it. We are planning to open source this sometime in future with Jupyter. So with this approach, we gain many benefits. One is with Unicorn, we now have application level aware scheduling. we have achieved significant cost saving through our better resource utilization. We have a comprehensive monitoring capabilities, and now this solution works both on on-prem and a third-party cloud, giving us more flexibility. So looking at specific features across our journey, so we see that we didn't have the cluster auto-scaling, dependency management, some of all the data lake concepts when we started with bare metal. We improved on that when we moved to VMware a solution, but at that time we lost the dynamic allocation, so which didn't help in improving our resource efficiency. With Kubernetes, our resource utilization improved, but it was still not up to the mark where we wanted, and we saw the advanced improvement with Kubernetes on Unicorn. With queuing support, we had it available on bare metal, but then we didn't have it with our VMware and Kubernetes, and now we still have it back with Unicorn. Our cost efficiency has moved from high investment utilization to best resource sharing with lowest cost. Gang scheduling, a critical feature for Spark, is now available with Unicorn. Resource fairness and job prioritization have evolved from basic to advanced with our current architecture. Now, key takeaways. I think to start with, if you are in your journey of moving from bare metal to Kubernetes, or you're already in that process, the first is you need to assess your current workload pattern, whether it's a batch processing or you need interactive or AI capabilities. This is really important to decide what kind of scheduling capabilities you will be needing, and then you can optimize on that. Design a phase strategy. Start with the hybrid approach. Migrate incrementally. Ensure you have proper test plans before migrating users, and which is running on your both previous infrastructure and the new infrastructure. Optimize resource allocation. So as we know, the kube scheduler is not meant for batch scheduling jobs. So this is one thing which you would want to consider from day one, like having a batch scheduler on top of the current scheduling capabilities which Kubernetes has. You would like to enable preemption policies to ensure if there are priority jobs has to be scheduled. Enable dynamic allocation, which we didn't have when we moved to VMware, and then we were beaten by that, because dynamic allocation ensures a more cost resource utilization. I mean, of course, there are cases like XGBoost where you don't want to enable it and you want all the executors to come up at the same time, but most of the cases you would like to enable dynamic allocation for better resource efficiency. Implement proper port scheduling. Kubernetes provide tons of configurations to ensure that your ports are placed at the right node. You can use node affinity rules, node selectors, taint tolerations to customize your Kubernetes specific configurations to optimize on scheduling. Handle your storage and networking challenges. If you have data sitting on local disks, you won't like to move to the distributed storage. And networking could be different. Like when we started, we had the bare metal only. The cluster was having access to only the HDFS, which it was connected to. So you would like to consider those networking challenges when you move from bare metal to Kubernetes. Configure proper configuration, proper shuffle service, whether you want to use external shuffle service or shuffle tracking. Some of the configuration might not be the same as you are as bare metal to Kubernetes, like CPU requested limits. When we started, we used to have a default configuration with putting limits as way higher than request, by which we got throttled because when you set it that way, only the one which has the highest limits take over, and you become the bad neighbor. So and we ended up setting both requests equals to limit to make it fair for better utilization. And yeah, this is the thing which you don't want to miss. Set up comprehensive monitoring. If you're using Unicorn, enable Unicorn's UI metrics to track scheduling efficiency. There's in terms of pitfalls and anti-patterns, yeah, I mean, as we said, you would like to enable dynamic scaling. There are cases where you would not like to do that, but yeah, don't forget to use the dynamic scaling, which is really efficient. Storage and networking changes might be tricky sometimes, so don't underestimate your storage and networking changes. And if you're using Unicorn, you might want to make sure that your scheduling policies are configured correctly, as it'll be tricky to debug once if you want your port to run at a specific queue or a specific location, it's landing in other place. It'll be tricky to find it out. So you make sure that you are configuring your scheduling policies correctly. Yeah, that's all. Thanks. Thank you all. Yeah. Questions? Yeah.
Do you hear me?
Yep.
Yeah, I would like to have two questions. First one is about data. So where do data lives in the Kubernetes environment? And the second one is there is no external shuffling service in the Kubernetes environment.
I can take the first one. Yeah, the data lives in cloud storage. So we're just in cloud storage. So it can be like local cloud storage, cloud storage. You think about like S3 or Ceph or these other technologies.
Okay.
So it's basically like getting things off of the HDFS clusters into a place where you can get good access to the data.
Okay.
Where it's still local, but then you can, if you're in different regions and things, you still have access to the data. So.
Thank you. The second one is no external shuffling service anymore?
Yeah, I think so. There's been some efforts to try to build that, but right now we're using mostly shuffle tracking. And we're really interested in like figuring out if there's going to be a great long-term solution for external shuffle tracking. Mm-hmm. Right now, we're not using anything specific. Yeah?
Okay, thank you. Hi, quick couple of questions. So at the last you mentioned don't underestimate the storage requirements. So we are also in the process of migrating Spark jobs from Yarn to Kubernetes. One of the challenges we are trying to solve right now is the ephemeral storage requirements that these jobs have. So we are looking at something like ephemeral volumes, for instance, but curious how you went about it and if that's a problem that you also faced.
Yeah, I think we did. Do you know more? You go for it, if you.
No, I mean, so we have different. So one is the Jupyter interface which we're providing for Spark, and where the Jupyter files lives, which is not typically the data, but the compute code which users want to use it. Yeah. So we are using like the Kubernetes persistent volumes for that one, but the actual data is the one which is residing on the cloud, like which is separate from the Kubernetes infrastructure.
Yeah, that part makes sense. Curious. So one of the requirements we have is really high throughput for part churn on Spark jobs, because several jobs wanting to run, we want to keep utilization high. Very similar system where we have a queue mechanism where jobs are queued all the time. When we looked into using persistent volumes, for example, the throughput slowed down significantly. Like we could maintain a throughput of about 200, 300 pods per second without PVs, but as soon as we put PVs in the mix, performance drops by like from 200 to 50 pods per second, max.
Yeah. We have the same problem, right? So,
how do you solve it?
Yeah, we use local disk, right? Use local disk as much as you can, and like configuring that disk correctly and using the right types of disk, right, is probably the best you're going to do, right?
I see.
Yeah. So like trying to you can also end up saturating the ability to actually mount the PVCs.
Yeah.
So like I would totally avoid that if possible. Right?
I see. Yeah. In that case, you're using just empty disk with disk. in this case?
Empty DIRs with disk, or you can configure more specific volumes, like in the size and shape that you need them. In our kernel configuration that Neha showed, you can specify the disk properties you want. And at scheduling time, we can get the right workloads to the right pods, or to the right nodes, well, with the right pod sizes, right?
I see. But in that case, do you use host paths as volumes or something else?
I can't remember what that is now, but let's connect after and I can get an answer for you.
Sounds good, thanks.
How has been your experience with shuffle tracking? Because we kind of ran into a few problems, so I'm trying to understand if we are the special case or it's kind of...
what type of problems did you run into?
Fetch failing at times, or executors staying around for longer than required.
Yeah, so we ran into some of those as well. Everyone's feeling the same pains.
Do you also use decommissioning?
I don't think we're using decommissioning. We do. We actually, so if I'm understanding decommissioning correctly the way you're asking it, so let me just kind of explain. As we're using shuffle tracking has to be configured well, right? And there's a lot of knobs that you have to like keep data cached in the executors, right? And then you have timeouts as well. So you can time out those things, and depending upon the type of interactive workload and the nature, someone may want to cache data. If they're just caching data, there's a cache timeout. And then on shuffle tracking, there's very similar concepts, right? So you may want to keep those nodes, those pods up for a certain amount of time. And then as you use dynamic allocation, the shuffle tracking will basically wane off because you're going to collapse the cluster, right? You're going to scale it down. So an example is like, I may start a cluster that has 2 pods, right, as executors and 1 driver, and it may end up scaling up to 100 pods, right? But then when I stop using it, I've stopped writing queries or doing data work, it can scale in, and then the shuffle blocks will end up being garbage collected, right? So when you're doing that, basically, if you're doing something really intense, you need to configure your shuffle tracking properties, such that for the nature of your workloads, your ad hoc workloads, that those shuffle tracking blocks stay around, right? Does that make sense?
Yeah, it does. And I think the dynamic allocation, as you said, is influenced by multiple factors, not just shuffle tracking blocks.
Yeah, for sure, yeah. I think there are 2 sets of things I want to talk about, right? So the shuffle tracking is one aspect of it, but then there's a set of properties to help you keep your executors around as well, right? Like when you go and you cache data, you don't want those executors to shut down because you've cached the data, you're going to reuse it. You might write one query and you want that data cached, and then you're going to derive another query off of that same data, right? So you're keeping the executors around, right, for a certain amount of time for your work. And then once you stop, then you have shuffle tracking that's going to start cleaning things up, right?
I think it's also quite relevant in terms of if you have complex Spark jobs.
Exactly.
Let's say if there are 6 stages that takes 5 hours, then in that case, that's where the shuffle tracking has basically given us the most pain.
Exactly.
I think the interactive workloads where data scientists, let's say, stop working, in our setup, the idle timeout for Jupyter notebooks basically kills the notebooks before shuffle tracking can even, downscale. So
yeah, so go ahead.
Yeah.
I'm going to finish and then I can jump in. I think I want to add a point. Did you want to finish that or?
I think.
Yeah, I think I will just say that for larger interactive workloads, I highly discourage using Jupyter notebooks, right? Anything that's going to run past 30 minutes, 30 minutes is even a lot, right? Anything that's going to run past 30 minutes, put it in the background. So we have the ability to basically build a DAG, and you all gave a presentation at Airflow Summit on the same topic. But we can basically schedule those notebooks to go in the background, so the users get the convenience of typing the code in the notebook, and then they can hit a few buttons and drop it in the background and run it on a schedule, or just stuff it in the background, and then the results will get generated, and the user will be notified that the results are there, right? And when you run those types of jobs, where you need to maintain the shuffle data for a longer period of time across multiple stages, you can tune the properties as you need to make that job efficient and things to not get collapsed in. But remember, as she showed on that last slide, let me bring the slide back. I think this one. You have on the, I think the right-hand side for you here, there is in the Q3, there's a batch workload. Once you put the notebook in the background, it becomes a batch workload. And your batch configuration with Unicorn needs to be tuned for those needs, right? Okay. So we have data scientists that will go do work and schedule things nightly or weekly. And we make sure that they put those things in a batch queue so that things get scheduled appropriately and they get the type of behavior they need in terms of long-running work. Right? Does that make sense?
That makes sense, yeah. Now you reminded me of another question that...
No. It's 6:05, so I want to be respectful to other people's time. Like, people don't need to stay, but I'd love to have you. If you want to stay, go for it.
Why did you separate out node pools for Jupyter pods, drivers, and executors?
Yeah, I think like Neha mentioned earlier in the talk. You want to take it? You take it. No, you take it. Sorry. I'm talking too much.
I think it was kind of mentioned the networking part between driver and executor. I'm kind of wondering, there are 3 layers in total.
Yeah, sure. So the Jupyter pod is kind of a long-running pod, right? So it doesn't require any special treatment in terms of scaling up or down. So we don't want to preempt these Jupyter pods. If any high priority job comes in, so they want to treat this differently than the rest of the Spark jobs, which has a priority setup. So that's why like we want this to scale up differently and don't want to mingle them with the rest of the Spark jobs, if that makes sense.
Okay, okay, it makes sense, thanks.
Yeah, I can also add a little more to that, like when you have drivers, right, when we connect to those Jupyter kernels, the driver is the kernel, right? And the driver, because that's the interactive component we're connecting to send the code to get the result, that pod we don't want to go down at all, right? So it needs to be in its own node pool, and the life cycle of those pods is different. The life cycle of the driver is there longer. The executors can come and go between multiple cells in the notebook. You're running different queries, right? So you may go from two executors to 100, and then back down to 50, and then back up to 100, and then back down to 75. So the churn rate in the node pool 3 there for executors is different, and your auto-scaling configuration can be tailored to the nature of those workloads. Does that make sense?
Can you give me specific examples of what those configurations are? Because I think that is the gist of the answer.
Let me think of specific configurations. Example would be, I'm trying to think, on the executor one is always the easy one, right? Which is like, I may need to, and I have people here waiting to maybe throw me out.
Sorry, we're running out of time.
Okay, running out of time. So last answer, and we can just sync up offline too. Ultimately, if you want to have, let's say, 100 nodes, and you want the equivalent number of pods on those 100 nodes, right? And at peak time, right, when people are running heavy queries, let's say they're coming in the office, they start running those queries, right? And then with dynamic allocation, that can scale in. It can scale, the nodes, you can go down to 10 nodes if everyone goes to lunch, right? And then it can scale back out when they come back in and start writing more queries. But let me answer the rest of that over here on the side of the stage. Thank you very much.
Thank you.